Hi student, today we are going to learn about the matrix vector and matrix algebra in R, because linear algebra is the integral part of the statistical analysis, and so unless you are quite familiar with the linear algebra, it is hard for a good computation in statistics without that particular parts of mathematical technique. So we have to be familiar with the use of different technique of linear algebra in R. So I'll start with the concept of vector and matrix in R and different vector and matrix operation in R, say matrix multiplication, scalar multiplication, matrix vector multiplications. And then the different aspects of statistical computation that might be the complication part can be overcome by the use of matrix and vector algebra. For example, we can use the matrix and vector algebra to calculate the correlation coefficient, the variance covariance matrix, without using any nested loops that might be required if we don't use the linear algebra. And few specific statistical computation that also I'm going to show how for that computations we can use the vectors and matrix algebra quite easily to get a quick results, avoiding the nested loops. Linear algebra is the fundamental notational technique used in multiple correlation factor analysis and structural equation modeling. Although it is possible to use R without understanding linear algebra, but it is very useful if you analyze the data through the help of vector and matrix concept. Linear algebra is a convenient notational system that allows us to think about data at a higher level rather than data point by point. The column of a spreadsheet or a complete spreadsheet can consider as a vector or matrix respectively. The high dimensional data can easily be handled by linear algebra in R. A column vector is a list of numbers stacked on top of each other. For example, A equals to say 2, 1, 3 are the three components of the vector, a 3 by 1 vector that I have assigned here. And a row vector is a list of numbers written one after other. For example, B equals to 2, 1 and 3. We make the following convention in what follows all vectors are column vectors unless otherwise stated. However, writing column vectors takes up more space than row vectors. Therefore, we shall frequently write vectors as a row vectors, but with the understanding that it really is a column vector. Let's learn how to assign a vector to a variable in R. Assigning a column vector to a variable in R, we normally use the function called C. C stands for column. So everything that you are going to assign in a vector, all the components should be passed within C function separated by comma. That is, A equals to C 1, 3, 2. And if you want to display, just write A, then you will see how it displays. And transposing a vector, just T is a function for transposing a vector or matrix. So you can pass the vector within T function, you will get the transpose of the vector the way it's shown here. If you want to multiply a vector by a scalar, you can use the asterisk symbol like A asterisk 10, and that will multiply all the components of the vector by 10. That is 10 into 1, 10, 3 into 10, 30, and 2 into 10, 20. If you want to sum all the, sum two vectors of the same length, you can do in the following manner. If A equals to say C1, 3, 2 and B is 2, 8, 9, that is 3 by 1 vector, and if you want to add up them, A plus B equals to, you can see easily that the component wise they have been added. So 3, 11 and 11. So A plus B can be easily, but provided A and B are of the same order, otherwise this operation cannot be possible, as you know. And if you need just inner product of the vectors, that is the component wise product, that you can again use the asterisk, that is a asterisk b, that will multiply say 2 into 1 2, then 8 into 3 24, and 9 into 2 18. So for inner product you can use asterisk. And if you want to sum of the inner product vector that is generated by the inner product, you can use the sum a asterisk b, that will give you the sum 2 plus 24 plus 18, that is 44. And if you need the norm of a vector, you can just use this formula. It's the square root of transpose of a into the matrix multiplication. This is a binary symbol that has been developed in R. You can use, you put the asterisk in between two dollar symbol that already defined in R. Is a binary symbol, stands for matrix multiplication. So you wanted to do the square root of a prime a, and that is a transpose a. That is what I did here, the square root of transpose of a into then matrix multiplication and then a, and that will give you the norms of the vector. The 0 vector and 1 vector can be assigned by the function replicate is rep, where the first element should be the 0 and second element the number of times the 0 should be repeated. So suppose you want a 5 by 1 0 vector, so you can write rep 0 comma 5. And if you want the 1 vector, similarly instead of 0 you replace 0 by 1, then you will get rep 1 comma 5. So 1 will be repeated 5 times. That means a vector that will have 5 elements, all of them are 1. Let's move to the matrix notation. To assign a matrix in R, we use the function matrix, and that first things that you have to do, you have to pass all the elements that you are going to assign to a matrix by a column, and then specify the dimension accordingly. It would be created. For example, suppose A equals to matrix C 1, 3, 2, 2, 8, 9. So C, within C column, that one column you are passing within the matrix function, and then you are telling n column equals to 3. If it is 3 by 3, it is a 3 by 2 matrix. So if you say n column equals to 3, automatically it will calculate the number of the other order, the number of rows. So as column is 3 and you have only, so we have 6 elements, so it would be 2 by 3 matrix that can be generated. And alternatively, you can specify just instead of column, you can specify just row, then it will automatically calculate the number of column and it will give you the desired matrix that you are looking for. One can find it easy to create matrix using R-bind because you get to enter the number as they appear in the matrix. That means first you have to create some columns, and the column can be binded, either R-bind or even sometimes you can use the C-bind too. So here I've shown one example with R-bind. R-bind one function that combine the two rows or two columns into two rows and give you a matrix. So first I'm entering two columns, say column 1 and column 2, and then ask for R-bind. It will give the R-bind, say C1, 3, 2 and C2, 8, 9. So same order, and it can bind one after another, and it will give you a 2 by 3 matrix. If you just use C-bind, then it will give you 3 by 2 matrix. The multiplication of matrix by a number, scalar, that is same as the vector multiplication. You can use the asterisk symbol, that is 7 into 7 asterisk a, that will give you the multiplication. Scalar multiplication means the 7 will be multiplied to all the elements in the rectangular arrangement or the matrix. The matrix can be assigned in this following manner. Suppose you want to assign a matrix of order 2 by 3, and the numbers are 1, 3, 2 to 8, 9, then we can write A equals to matrix. Matrix is a function that assign matrix to a variable. So matrix, and then all the elements should be passed through one column function, that is C1, 3, 2, 2, 8, 9, and then you specify the number of columns. You can specify number of columns and number of rows, but if you specify the number of columns and that is sufficient, it automatically can calculate the number of rows and you can display A. Similarly, if you just specify the number of rows instead of number of column, automatically it will calculate the number of columns and assign the matrix as per your need, and you can display the matrix A here. Just type A, then it will display the matrix. One can find easier to create the matrix using either C-bind or R-bind, and that is, suppose you have 2 or 3 equal length of rows or columns, then you can use R-bind to combine them into 2 rows, 3 rows, or C-bind as combine the column, so 2 or 3 columns together, but provided they have the equal length. Say, for example, suppose you have 2 vectors, A1, 3, 2, and another vector as elements 2, 8, and 9. So you can easily write R-bind C1, 3, 2 and C2, 8, 9. Then it will combine into a 2 by 3 matrix. Or alternatively, you can use C-bind. In C-bind, then it would be 3 by 2 matrix. And if someone wants to multiply a scalar to a matrix, it means that scalar will be multiplied to all the elements of the matrix. So you can similarly, like vector, you can use the asterisk, say 7 asterisk A. So automatically the 7 will be multiplied to all the elements of the 3 by 2 matrix. The transpose can be done same as the vector that we have seen. Just T function we will use. So if it is 3 by 2, then it would be 2 by 3. So transpose A equals to, if A was 3 by 2 matrix, then transpose A will give you 2 by 3 matrix. Similarly, if you want to sum 2 matrix of same order, then you can use the plus symbol. Say, suppose you assign another matrix B of 3 by 2 matrix, and previously we had A 3 by 2 matrix, so we can add up A plus B will give you the matrix addition, that element wise it will add. The multiplication of a matrix or a vector, that is the vector multiplication or matrix multiplication that I told earlier, that the one binary symbol is there, that is the asterisk is the asterisk in between two dollar symbol, that is a binary function that already defined in R. So suppose A is transpose of A, that is and then A multiplied the matrix multiplication, say dollar asterisk and dollar and A. So A is a small a is a vector, so automatically it will give you a vector multiplication, and that as it is a 2 by 3 and 3 by 1 2 by 3 matrix and 3 by 1 vector, so automatically the results will come as 2 by 1 vector. So multiplication of a matrix, so matrix multiplication, it will follow the rule of matrix multiplication is that the number of columns should be equal to the number of rows of the second matrix. So the same binary function that defined in R, the asterisk within dollar symbol, $2 symbols, so can be used. A matrix multiplication B will give you the matrix multiplication. To assign a 0 matrix and 1 matrix, so 0 matrix, you can just write matrix 0, specify the number of row and number of column, automatically a 0 matrix would be assigned. Similarly for 1 matrix, matrix, you can just write matrix then 1 comma number of rows and number of columns. Here say number of rows is 2 and number of columns equals to 3, automatically it will generate 2 by 3 1 matrix, the unit matrix. For diagonal and identity matrix, for diagonal we can use the function diagonal DIAG, where you can pass the diagonal elements, automatically it will create a diagonal matrix. So if you pass 3 elements, it will create 3 by 3 diagonal matrix. And similarly, if you want the identity matrix, you use the diagonal DIJ, the diagonal matrix function, and you just pass 1, 3. That is, first one is diagonal elements, and the second one, second argument is 3 is the order of the matrix. So if you write DIAG, then 1, 3, that means it will create a diagonal matrix of 3 by 3 order, where the diagonal elements are all 1. So that way you can create the identity matrix. The determinant of a matrix, a square matrix, is actually can be calculated by the DT function. So just if you have a square matrix, just pass the square matrix within DT function, automatically it will give you the determinant of that matrix. Now we'll move to some statistical derivation based on matrix and vector methods, because that will help you to understand how you can use the matrix and vector algebra in a statistical computation in R. I mean, basically it is very useful, as you might be aware that R sometimes become very slow while you use the nested loops. We can easily avoid the nested loops by vector and matrix multiplications. So let's see one examples that I'm going to use first. Is trying to get a matrix deviation score. Just subtract the mean vector from each cell, and that can be done by existing function scale. So what I'll do, I'll grade the work done by an existing function, and then I'll show how you can use the vector and matrix algebra to calculate this, avoiding any kind of loop. So suppose x by x, double x is a matrix of 4 by 4 order, and if you just pass that matrix within scale, and in the argument just write scale equals to false. So that means normally the scale actually standardize the data, and if you specify scale equals to false, that means it will subtract the mean but won't divide the variance. So that way you will get what you are looking for. So this way we can get the matrix deviation score just setting scale equals to false in the scale function. So if you just need the standardized data, just say scale equals to false, or by default scale equals to true. So if you just need the standardized data, then you should either specify scale equals to true or just leave as it is, and automatically by default it is true, so it will give you a standardized data along with the column mean, and the column standard deviation will be provided at the end of the standardized data, as you can see here. We can use the DIM function to find out how many cases, number of rows and number of columns. So if you just write DIM and within that you pass the matrix as the argument, then it will give you the number of rows and number of columns. Suppose you have 6 by 4 rows. Alternatively, one can use number of n row and n column, n row and n col function to get the same of the row and columns respectively. Say n row double x, that will give 6, n column double x, that will give you 4. To get the sum of the columns, we multiply one vector to matrix as follows. Suppose you want the sum of the columns of a matrix. Existing functions are there, but I just trying to show how you can use the vector concept or vector matrix concept to get some derivations, avoiding loops or existing functions. For example, you should write 1 equals to replicate 1 in n rows of double x, that will give you one vector, and then transpose of 1 with matrix multiplication with double x, and that will give you the sum of the columns. To get the column means, one can divide the return vector by the number of rows in this following manner. Say x mean equals to T1, then matrix multiplication, and then double x divided by n row of x. That will give you the column means. Similarly, you can calculate the row means, so you can do it on your own. To form a matrix deviation scores manually, one can do that by say x dot diff equals to double x minus 1 matrix multiplication x dot means, and that will give you x dot diff, and that is actually what you are looking for. You can compare with the earlier function that we have earlier derivations that we have generated by the scale function, setting the scale equals to false as the argument. Some statistical deviation, a few more statistical deviations we can look for, like variance and covariance matrix. To derive the variance and covariance matrix from a design matrix AX, one can follow the direction below. We first generate a random matrix for demonstration as follows. Say set sheet 42. I see just setting the sheet to get the same matrix every time. And say x equals to matrix of order 6 by 4, so 1 to 24, and n column equals to 4, and then give the dimension name of the matrix. The row dimensions are S1, S2 or S6, and column dimensions as V1, V2, V3 and V4. So x is a matrix of order 6 by 4. Now, to get variance covariance matrix, we first assign one vector, that is replicate one REP1 in number of rows of x in row x. Then x dot mean equals to, this is the way that we have calculated earlier, transpose of 1 in matrix multiplication x divided by n row of x. And then x div is x minus 1 vector multiplication x dot means. That will give you x dot diff. If you can type it x dot diff, it will show you what you got by these derivations. And compare this result to just using the scale function to mean center the data. You can just say scale equals to false, then automatically it will give you exactly the same results that you calculated based on the matrix and vector concept. See, x covariance can be then derived by x dot diff variable that we have defined, that is the deviation variable, and that is transpose of x dot diff, then matrix multiplication x dot diff divided by n row of x minus 1, that is n minus 1 that we normally divide, and that will give you the covariance matrix x dot cov. Suppose someone wants to calculate the correlation, that also can be done by vector matrix concept, avoiding the correlation functions. The correlation functions is there, you can always use, but this is some cases I am demonstrating might be useful in the future high dimensional computation. Say assign a diagonal matrix x dot var of the diagonal of x dot cov matrix earlier that we defined, and then SDI equals to diagonal of 1 by square root of diagonal x dot v. So diagonal matrix square root, if you take that 1 by, that will give you the inverse. And then column names and column row names can be assigned as earlier. The round of by just 2 significant digits, if you want to take, you can take SDI. The SDI matrix will provide only the diagonal element should be there, off diagonal should be 0. And then to get the correlation, one can use this expression, say SDI, then matrix multiplication x dot cov, then again matrix multiplication SDI, and that will give you the correlation. You can assign the same row and column name labels of the matrix, and then finally you will round it by 2 significant digits, will provide you the correlation coefficient in the correlation matrix that easily can be done with the COR function. The core, the COR1 function is there. If you pass the matrix, it will give you this correlation. I just showed here how you can do manually by vector and matrix algebra, avoiding the loops. Hope you know that this particular concept might helpful in your future calculations. So this is not the end, I'll include one more module in this sequence to get a complete idea about the application of vector and matrix in R. So we have learned about the vector and matrix application in R, and as we have seen that R variables are normally either vector or a matrix. So inherently, R adopted the linear algebra in its code itself, and then we learn how to use the matrix and vector operation in R, matrix multiplication, vector multiplication, and then we have seen the different complication in computation can be resolved by linear algebra, the matrix and vector application of matrix and vector operations, and that I also shown few specific computation that can be easily done by the matrix algebra without calling for any nested loops. That, as you know, that R can make the programming speed very slow if you use any nested loop. So the key for making R computation fast is to use the vector and matrix algebra in R. That might be very, very useful. My guess is this module might help you to really understand how the vector and matrix can be used to make your statistical computation faster.